Hello everyone, I hope you're doing well. So in today's video, I'm actually going to walk through the VCA sample paper for the Maths Methods Exam 2. I've heard a lot of students, complaining that there's no solutions to this question. There's, a new part they've put in the study design, such as, pseudocode. And yeah, I'm going to have a walk through this paper. I've not touched this paper. This is quite new. So yeah, let's have a go at it. So let's try the multiple choice question. Okay, question 1. We have two equations. Okay, these two equations. Whichever following correctly describes the general solutions to the systems of linear equations given above. Okay, look. One way I would do this question is there's two ways. I'm going to do it, the first way is I'm going to do it by calculator. So what I'm going to do by using the calculator is, I'm just going to rule this over here. This is where I'll be using my CAS. Okay. So what I would do is I would go on menu, I'll go on algebra, solve systems of equations, and there is 2, and I'll put the variable z also. Okay. I'll write both of them, so x minus 2y equals 3, and 2y minus z equals 4. So we get we got 3 general solutions. Okay, so we get x equals, that C2 actually just means k. It's like an integer value. So k plus 7. Y in this value is k plus 4 over 2. And z equals k. Okay. So why don't we not, let's let, for this example, let's let k equals -7. So x will become 0 in this one. Y will become, so 4 minus 7, that will be -3 over 2 here. And z will become -7. Okay. Now, because we know this, because we know these values over here, what we can do is we can do this. All of the multiple choice solutions have x equals k. But for our one, we know that x is actually equal to 0. So let's say for these solutions over here, let k equals 0. If we let k equals 0, y value should give us the same, and the z value should give us -7. So let's try to check them out. Okay. Let's try y, the first one over here. So y is equal to half. Our k value is 0, so that's just 3. So it will be 3 over 2. No! This is -3 over 2. So anything that has that plus, so this one has a plus here, so that's wrong. Also, this one's wrong, and E is wrong. Okay, that's a quick way. Let's try to find which one, C or D. Okay, because we know that, let's look at Z. Let's try this one over here. Let's sub it in here. So Z is equal to, because K is 0, we can say 7. But Z is equal to -7, so it must be D as your answer. So D should be your answer. That's actually a way to do it. The CAS can help you out because, yeah. But let's now try doing it by hand. So, by hand. It's not an actual hard equation to solve by hand, but let's just try it out by hand here. So we know our answer is D. So by hand, what we can say is the first equation here, so this first equation here, and your second equation, the first equation has just x. Because we know x is just equal to k for all of them, let's sub it in to the first equation. So we're saying k minus 2y equals 3. And let's solve for y. And that'll be 2y, 3 minus k. Sorry. K minus 3. K minus 3. So y becomes k minus 3 over 2, which is equal to half k minus 3. So, yes, so we can actually, again, take all of those out. It can only be C or D. And now, because we have y, we can actually sub it into this equation to find z. So we can say 2 times y, which we can get rid of that half anyway. So it'll be k minus 3 minus z equals 4. Z is therefore k minus 3 minus 4. Therefore, k is -7. So, yes, both ways work. So, I hope It wasn't too bad, this question, but yeah. Let's move on to the next question. I hope that's right. Okay, question 2. Newton's method, I'm just going to change color. So Newton's method is being used to approximate the non-zero x-intercepts of the function with the equation f of x, okay, this. An initial estimate of x0 is equal to this. Which of the following gives the first estimate that would correctly approximate the intercept to 3 decimal places? So which of the following gives the first estimate that would approximate the intercept to 3? Okay, so what I'm going to do is I'm just going to create a new document. Okay, so I'm going to first define f of x. That's what I'm going to do. So let me first define f of x. That will be x to the power of 3, 5 minus root x. Okay, perfect. And what I can do is, because I know x0 is 1, I can make up, so I can define another function. So let me define another function, g of x. Whereas this g of x is actually our equation for Newton's method. So it'll be g of x naught, x naught minus f x naught over f dash x naught. So let's put that over here. So that will be 1 minus, actually not 1 minus, x minus f of x. F of x, and the derivative of f of x. Perfect, so we've defined it, and now what we can do is actually start finding out what are the values. Okay, so let's try out the first one. So we know that x0 is 1, x1 is what? We can say g of 1. If we sub in 1, gives us 9. Okay, what about x2? We can say that g of 9 is 6.0.05. Okay, we have to actually approximate the intercept of 3 decimal places. So let's actually first solve f of x. So let's first solve to find the actual f of x equal, to find the actual solution. And it's this one here. So it's 1.90. Okay, let me just write it on top of here. So we want to get approximately 1.90 4 to 4 decimal places. Let's continue what we were doing. So g, now we sub this thing in here, we get 4.12. So 4.12, x4 would be, again, g, sub that in again, 2.92, x5 is g, again, sub that in, 2.24, x6 is g, again, put the answer there, 1.96, so we're getting actually closer. What about x7? So g, let's sub that in there, 1.90, okay, we're getting very close, so 1.9, so if we, 3 decimal places, that's 1.906, nope, so it should be the next one, so just sub that in there, 1.90, so it must be 8, so 1.90, we get 1.904, perfect, so the answer should be C for this one. Yeah, it's a pain to use the calculator for this one, but yeah, we have to use our calculator. So let's move on to the next equation. Question 3. The area between the curve y equals 1 over, this here, and the x, let's change it to color, and the x axis on the interval from 0 to 4 has been approximated using the trapezium rule as shown on the graph. Using the trapezium rule, find the approximate area calculated. Okay, not too bad. So the first thing that I'll use is by using the trapezium rule is to find how the width. So the width goes by 1. So we can say 1 times f of the first part, which is your 0 here, f of 0, plus double your 1 here, so that will be f of 1 plus 2 f of 2 plus 2 f of 3 plus f of 4. We don't actually double that f of 4. It's because it's at the end. So can you see how it ends? So the initial and the ending don't actually get doubled. And we don't want to forget that half over here. That half is, again, it's from the area of a trapezium. If you remember, the area of a trapezium is half a plus b c. It's that half we don't want to forget. All right. And now what we can do is, okay, we can just a little bit simplify. What's half times 1? Just put half. What's f on 0 here? So let me actually just, okay, define the actual function. Let me define it. So let me just make a new document. Let me delete that. Okay, let's define f of x for this one. Equals 1 over 27 x minus 3 squared x plus 3 squared plus 1. Okay, so what's f of 0? It's 4, so we can say 4 plus, what's 2 f of 1? It's 1, 8, 2, 2, 7. So if we're looking at the solution, so it's half. They all have half. They have a 4. 1, 8, 2, 7. Okay, let's plus. What is 2 f of 2? We get 104. So 104, 27 plus 2 f of 3 plus 2 plus f4, which is 76, 27. Okay, which one gives that? Looks like B is your answer here. So B is your answer. Is that true? So 4, 127, 104, 27 plus 2 plus 76. Yep, looks like that's the answer. Let's go to the next question. Question 4, the probability density function of a random variable x is given. Okay, find the value of a such that the probability of x is less than or equal to a equals this. Okay, what I'm going to do is 5 over a, I'm just going to make it into a decimal. So let me rub this. Again, let me delete this, create a new document. So 5 over a is actually equal to 0.625. Okay. It means, let's try, and so let's find the area of this part of the equation here. Let's find the area of that. So we're saying from 0 to 4, x plus 1 over 20 with the respect of the x equals, let me use the calculator for that. Okay, not this one. Okay, so 0, 4, okay, x plus 1, 20, x. Okay, we get 0.6. Okay, so the value of a is actually between this domain, right, and this domain over here. So what I'm going to do is I'm going to say 0.625 minus 0.6, which is equal to 0.025. It means this area, so we can say that from 4, so from this point here, 4, to the value of a of the function 36 minus 5x over 64 dx should equal 0.025, this leftover. Is that true? So 36 minus 5, okay, because we've minus that, okay, so 4 to a, dx with 0.025. Okay, let's calculate that, and that should give us the value of a. So let's solve for a. Let's use our calculator. So that will be, again, 4 to a, 36 minus 5x, 64 dx equals 0.025. which gives us this, and we can solve that. So solve answer, comma, a. Okay, we get two values of a. We get this and that. Let me just get into terms of decimal points. Okay, we cannot use a equals 10.298. It's because the max is 7.2. So your answer should be this one over here, which is this part here. So that will, if we expand that, so -4 15 plus 36 over 5. Which one would it be? Looks like C is your answer. Yep, C is your answer for that one. Okay, let's move on to the next question. Oh, now we're getting into pseudocode. Okay, so to actually do well in pseudocode, what you want to do is you want to follow the instructions very carefully. It's like following simple steps. Like, yeah, so let's just have a look at this. I've done some questions before, but this is a new one from the book. But yeah, now let's try to apply everything together. The algorithm below described in a pseudocode estimates the value of a definite integral using the trapezium rule. So f of x is our function. To integrate, a is the lower terminal of integration, b is the upper terminal of integration, and it is the number of trapeziums to use. So define the trapezium as f of x, a, b, n, okay? And we are given some steps over here that we need to follow. Let's just read the question. It says, consider the algorithm implemented with the following inputs. Okay, now we have an equation. This is our input. The value of the variable sum after one iteration. So one iteration of the while loop would be closest to. Okay, so the value of the variable sum after one iteration. So one iteration pretty much means one repetition, which is just do this whole step once. That's what one iteration means. One repeat. Okay. So how would you, okay, one repeat. So what I'm going to do now, let's do that. And we want to try to find that sum. So consider the following implemented. Okay. The value of the variable sum. So we want to find this value over here. I think so. Let's try to do that. Okay. Let's follow the steps. So the first step is H. Can you see the arrow? Always make sure the arrow, just right when you write it, just write it like H equals. Make sure the arrow just like means equals. H equals B minus A. Now what do we know? This is A, this is B, and this is N. So B minus A is 3 minus 1. So what's 3 minus 1? That's 2 over 10, which is 1 over 5. So our H value for this one is 5. Okay, I'm going to just put it over here. That's the first step done. We can tick that. Now it says the sum equals f of a. Now means that the log e of a, which is 1, plus log e of f of b, which b is 3, so 3 is, I know this one over here equals 0, so the sum is actually just equal, your sum is equal to, if I'm going to write it, so what's the natural log of 3? It's, okay, 1.0, it's 1.098. I'm just going to rub this off here and just keep that one over here. This value over here. That's done. We can tick that. Now, it says x equals a plus h. What is our a value? So 1 plus h, which is 1 plus 1.5, which is 7 over 5. So that is our x value. Let's rub that off. Write it over here. Put it over here. Is that true? So again, 1 plus 1 over 5. Wait, 1 plus 1 over 5. 6 over 5. Oh my god, what am I doing? Okay. 6 over 5. Yep. Okay, let me just have a look at this code again. So f of a. F of a is this. And 1 plus h. Okay, yeah, 6 over 5. Perfect. Yep. That's your x value. And your I is equal to 1. While I, now let's follow here. While I, so which is 1, so 1 is less than n, and our n value is 10. Is 1 less than 10? True. Yes, it is. Then we must do these steps here. These steps over here. The sum, your sum, this is a new sum, by the way, is actually equal to your previous sum, which is over here, 1.098 plus 2 times f of x, which is log e, and what's our x value? 6 over 5, so 6 over 5, which should equal, let me just do that, so my calculator, let me just take this over here, 1 plus 2 times, oops, plus 2 times the natural log of 6 over 5. That gives us 1.47. 1.47, or 1.63, sorry. That's your new sum. Okay, that's it. That's it. That's the value of the variable sum after one iteration. We've done it once, and yeah, we don't have to do these extra steps here because we don't want to find the area. But yeah, that's it. We found that sum, which is 1.46. I'm hoping there's one. Okay, 1.46. I think it's C then. All right, this was a new question. Wow. So, okay, to do these questions, all you need to do is just follow the steps carefully, one by one. Okay, let's go through the next. Okay, another one. Consider the algorithm below, which uses the bisection method to estimate the solution to an equation in the form of f of x equals 0. Inputs. Okay, is a function of where x is in radians, a is the lower bound interval endpoint, and the upper interval endpoint. Max is the maximum number of iterations. Okay. So, max is, okay. So this value over here, this max value, is going to give us how much times we have to repeat this code, repeat this algorithm. So, okay, we have a number of steps here. I'm not going to have a look at it right now. I'm just going to look at the question. It states, the algorithm is implemented follows. Bisection, so we have sine is our function, a, this is your a, this is your b, and this is your max. We want 2 iterations, actually. So we want 2 times to repeat this code. The value would be returned when the algorithm is implemented as given. Okay, not bad. Let's follow this. Okay, let's do the first step. Okay, if f of a, so we're saying that if sine, our a value is 3, times sine of 5 is greater than 0. Let's check if it's greater than 0. Let me just write it on my calculator. So sine 3 times sine 5 is equal to negative. It's a negative number, so it's actually not greater than 0. So if it was greater than 0, we would return an invalid interval. So because it's not, we can move on to the next step. It says I, okay, I'm just going to rub this here. Okay, it says I equals 0 for this one. While I, which is 0, is less than max, our max value is 2, is 0 less than 2? Yes, it is. So we can actually follow the next step. So we can tick that. So your mid value, your mid is equal to a plus b, which is 5 plus 3, which is 8, divided by 2, which is 4. Your mid value is 4. If mid, so f of mid, so we're saying that sine of 4 is actually equal to 0, which I don't think that's true. So let me just write it. Sine of 4. No, it's not actually equal to 0. So I'm just going to rub that off. So if it then return mid, but because this is, it's not true, we can move on to this else if. So we have to move into this part here. Else if f of a, so sine of 3 times sine of the mid value, which is 4 in this case, is less than 0. Let's try to find if it's less than 0. So that will be sine of 3 times sine of 4, which is less than 0. That's true. It's a negative, it is less than 0. So we can then follow this part here. B means that B must equal to your mid value, which is 4 in this case. And yeah, else, blah, we don't actually need to follow this one because this is like what happens if it wasn't less than 0, we would follow that one. But yeah, now let's look at this. Now the new value of I is equal to the original one, so this one here, so 0 plus 1, which is 1. So our new value of I equals 1. Now what we have to do is repeat the whole code again, because that's when we need to do it twice, because there's 2 iterations. So let's try to repeat the code again. So let's start from here. So let me just rub that all off. Let's start over here. So I, so which is 1 here. Is it less than the max 2? Absolutely. So move on to the next code here. So mid value is equal to a plus b. Because our new value of b, by the way, here, be careful. Our new value of b is 4. So what we're saying is a is the same. So 3 plus 4, which is 7, divided by 2, which would be 3.5, if I'm not mistaken. So that's our mid value. So if f of mid, so here, now the next step, is sine of 3.5 equal to 0. I don't think it is, but let's just have a check. 3.5, it's not equal to 0. It's a negative number. So then we have to move into this next step over here. Else, okay, else if f of a, so again, so we're saying that, let me just write this over here. Sine of our value is 3 times sine, our mid value, is 3.5. Is it less than 0? Let me try to have a look at that. So sine of 3 times sine of 3.5. Yes, it is less than 0. So that's good. So we can move on to this step here, which is therefore b is equal to your mid value, which is, our mid value is this one over here, 3.5. And that's it. We've done 2 iterations, and so your final answer is this one, which is D in this case. Wow. Look, I'm not going to lie, these questions, these coding questions, or these pseudocodes are a pain to do. Wow. Okay, another one. One way of implementing Newton's method using pseudocode with a tolerance. Okay, what I know about tolerance value, sure, when I see that word, tolerance, it's in use in physics also. Tolerance, every time you hear that word, just always put plus or negative. That's all I remember. That's all I used to do in physics. Tolerance, when you see that word, tolerance, it means plus or negative this value. Is shown below. The pseudocode is incomplete, with 2 missing lines indicated by empty boxes. So f of x is a function of x, x0, an initial estimate for the x-intercept of f of x. Newton's, define Newton f of x, x0, makes sense. So df f of x is the derivative of f of x. I is 0 equal to 0, and your previous x is actually equal to x0. Makes sense, yeah. So while I is less than 1,000, which is true, 0 is less than 1,000, do this. Okay, if you guys are not understanding what's happening here, it's pretty much saying our prev of x is equal to x0. That's what it actually means. And our next of x is equal to your x1. So normally the formula that we use is this. We would normally use x1 is equal to x0 minus f of x0 over f dash of x0. So let's see here. Look at this. So the next, which is, again, what's next? It's this one, x1. So we're saying that x1 is equal, remember arrows means equals, previous of x, which is x0 minus f of previous. So it's pretty much the same as this right here. That's what the programming is doing. That's what the code is doing. So what are we trying to find? Okay, so there is which of the following options would be most appropriate to fill on the boxes. Okay. Okay. What does a tolerance level mean actually? So the tolerance level is where you want the value of the difference between the x values. So the difference between x1 minus x0 to b. So like it must be between 0.001 and negative 0.001. Again, that plus or negative means these values, the difference between these values must be between there. So I think that's what these codes are doing. So if next means x1 minus x0 is no, this one's wrong. It needs to have this kind of wrong. Okay, look at these over here. Negative 0.01. Okay, so the difference is the return value we get. It must be E. Why would we even have a previous? So why would we want to return to X? No, we always return to the next value. So X1, X2, X3. So why would we, yeah, that would be. Look, this, I'm not gonna lie. I've seen this question before. It was, I think, in the Cambridge textbook. So yeah, they would normally use tolerance for if you're going to do Newton's method, there is some coding in pseudocode. They use tolerance value, and it has to be, the difference between those X values must be between the, yeah, I've seen that question before, I'll be honest. It's not good. I don't even enjoy these questions. I'm just hoping that I finish them. Okay, done. Okay, these pseudocode questions are so ugly, I'm not going to lie. They're quite difficult. They're very long. Okay, now let's actually get into section B of the exam. The function g is defined. Okay, we can see that here we have a restriction on the domain, and here's our function. So what I'm first going to do is I'm going to go on my cas, and I'm going to add calculator, and I'm going to define the function g of x equals 3 natural log of x minus x. Done. Sketch the graph of g on the axis below, label the vertical asymptotes. Okay, so we have vertical asymptote with its equation, and label any axial intercept. So axial intercept, stationary point, end points of the coordinates to 3 decimal places. Okay, 3 marks. Let's do that. So the best way that I'm going to do this question is actually by, if I go on my cas and go on graphing, I can write g of x, and I'm going to restrict that domain because we want it from 0. So 0 less than x, less than or equal to 7. And we get this. This is our graph. Okay, we can see that there's straight away an asymptote at x equals 0, as we can see. So I'm just going to draw that so I don't forget. X equals 0. I think you can't see it, so I'm just going to rub that off and use a red here. So x equals 0. That's your asymptote. And what I'm going to do is I'm going to just try to there's actually, the thing about the T-Inspire CAS calculator is you can actually do this, and it's so helpful. What you can do is, if you can go to view, you can go to grid, and you go to aligned grid. And what do you want to else do is go to Windows, Zoom, and Windows settings. Your x minimum, we want it to be, what does x min means? When you look at the x axis, so this x axis over here, we want it to be, what's the most least value, which in this case is 0. So we can put 0. What's our max value? We can see 7 is our max, but I'm going to put 8 because it looks like an 8 here. So I'm just going to put that 8 here. And what's x scale mean? X scales, what are the scales? Well, the scale is from, they all go by 1, these scales. So the scale is 1. Okay, so I'm going to write that. And I'm going to do that for y min. So what's the most least? It's -2. Your y max is 1. And your auto scale, which is it's going by 0.5 each. So I'm going to press OK. Okay, here it does it for me. It's given everything to me. So what you're looking at your CAS right now is you can just copy everything that you have on this screen. It's all up to scale, by the way. That's the beauty about this question. So I'm just going to copy that. So I know that there is an intercept here. And so that's 2, 3, 4, around here also. And I know there's going to be a cross here. There's also a cross here. And it's going to be at the ending here. There's going to be like a over here also. As this goes down, there's going to to cross here. It's going to cross over here too, over here, and over here. So what I'm going to do is I'm going to follow that nicely and smoothly. I'm going to follow that. And perfectly. That's it. So I followed it perfectly. I'm just going to, yeah. And I'm just going to go, this goes to infinity, by the way. Make sure you put an arrow. You don't want to make sure it looks like a endpoint. So yeah, we've done that. That's nice. Now what we just have to do is, okay, the first part is we've labeled the vertical asymptote with its equation and label any axial intercepts. Okay, I'm going to go back to my calculator and just say, solve g of x equals 0, comma x. We get two values. We want it to 3 decimal places. So this over here, I'm going to write it as coordinates. So it's going to be 1.857. And the 0, 0. And this point over here is 4.536, 0 to 3 decimal places. Okay, we've done that. And we also want to do the stationary point. So the stationary point is we want to solve for the derivative of x, of g of x, equals 0, comma x, and we get x equals 3. So at x equals 3 here, so at this point over here, 3. If I sub it back into the equation g of x, so 3, we get 0.29296. That's also your stationary point and your endpoints. Endpoints are very easy. So because this endpoint over, so we only have one endpoint, by the way. So this endpoint would be 7. I'm going to shove 7 into the equation. It's negative 1.162. Okay. We've done that. I think that's right. I hope it is. That should be it, yeah. That's it for that answer for this one. Okay. Question B states, find the equation of the tangent to the graph of g at the point of x equal. Okay, this is easy. 1 mark. We just need to give, okay, what you can do is use your calculator. Go on menu, go to calculus, go on tangent line. Write the function, which is g of x, comma x, comma. What is the x value we want to find? X equals 1 in this case, right over here. So, put 1 equals, we get it. So, y is equal to 2x minus 3. Next equation. Sketch a graph of the tangent to the graph of g at x equals 1. Okay, so we need to draw this tangent. Now, because of the tangent, I'm just going to draw in a different line, like a red line, is at x, so it's at this point. Oh, no, sorry. It's at x equals 1, which is, yeah, at this point over here. And I want to draw this tangent. I'm going to use a ruler. I'm just going to use this ruler to help me out with this. Okay, so it's around over here. Just perfectly here. What I'm going to do is I'm going to draw this just like this. Just like this. Okay, I mean, that's it for this one. Okay, I don't need the ruler anymore. So here's your tangent. So it touches at this point, and it goes. Okay, here's your tangent. And what else do we need? So sketch a tangent on the axis. That's all we do. We need to sketch it. We don't actually have to write the coordinates, I think so. Yeah. Perfectly. Okay, that's it. That's done. Newton's method is used to find the approximate x-intercept of g with an initial estimate of x not equals 1. Find the value. Okay, we know that x1. I'm just going to use this by calculator, actually. Don't even need to do it because it's only 1 mark. Don't need to show working out. What I'm going to do is I'm going to define a new function. F of x is equal to x minus g of x over the derivative of g of x. And what we want to try to do is we want to find the value at 1, which gives us, sorry, I did not even define, define this here. Now we can sub f1. Okay, 3 over 2. So x1, 3 over 2. That's it. Find the horizontal distance between x3 and the closest x-intercept of g, correct to 4 decimal places, and the closest x-intercept of g. Okay. So let's first find x3. Well, we know that x1 is 3 over 2. So what we're going to do is, so x2 would be f of 3 over 2. So, yep. And so x3 would be f of this value, put it inside the function, which is 1.853. So, let me just drop this over here. So your x value, x3, is 1.8535, blah, blah, blah. And what is the closest x-intercept? Okay, I'm just going to solve it. So, solve g of x equals 0, x, and this one's the closest one. So what I'm going to do is it larger? Yes, it is. So I'm going to take this value, minus it from this value. That gives us this over here. So your distance, your d, is equal to 4 decimal places, so 0.0036. Yeah, that's the solution for that one. Find the value of k where k is greater than 1, okay? Such that the initial estimate of x0 equals k gives the same value of x1 as found in part C. So what's x1? 3 over 2 from part C. So we want 3 over 2, so we want x1 to equal like the first initial estimate. So what we want to do is, well, we know the formula again. Let's rewrite the formula. So we know that x1 is normally x0 minus g of x, g of over g dash x naught. And we know that x1 in this part is 3 over 2. And our x naught here is k. So we can say k minus g of k over g dash k. So if we use our calculator, we can actually just calculate the value of k. Let's do that. So what we want to do, and so we can just say 3 over 2, so 3 over 2 is equal to, because we've already defined f of x as to be in that Newton's method, so we can say that f of k, comma x, comma, no, yeah, which we get this, and we want to solve this over here, comma k, where k, we want to make sure we restrict k, where k must be greater or equal to 1, or greater than 1. Enter, and we press Control Enter. All right, we get this value over here. So k, which is yeah, perfect, to 3 decimal places. So 2.397. Yep, 3.97. Okay. Using the value of k, sketch the tangent to the graph of g at the point where x equals k on the axis. Okay, no problem. So just sketch it. Okay. So perfect. That's no problem. So, okay. Our value is 2. So what I'm going to do is, I'm just going to, again, I'm going to find out. So 2.397. So if I'm going to go here, 2.397 is approximately over here, this part here. So I'm going to use a ruler, and I'm just going to make sure that tangent touches perfectly. So just over here. All right. And I forgot to actually label them. So let's let this, yeah, we need to probably label them. Do we? Yeah, we probably do. So I'm going to just label them. So I'm going to just name this as like y2 equals. So I'm going to find the equation of the tangent by using my calculator. Calculus tangent line of g of x, comma, this value over here, which is like, I don't know, like 0.25 x minus 0.37. And I'm going to also name the equation of the pink line, which was the tangent line at 1. So I'm just going to put this here, which was 2x. So y1 is 2x minus 3. And this graph here, g of x, is actually equal to, over here, 3 log e of x minus x. Perfect. I hope that gives us the mark. Okay, now we're up to question 2. All right. Jack and Jill have built a ramp for their toy car. They will release the car at the top of the ramp, and the car will jump off the end of the ramp. The cross-section of the ramp is modeled by the function where... Okay, so here it is. So we can see it's a straight line at x equals 4. So yep, so if I look at this graph, so when it's 5, so over here, it's a straight line. Okay, perfectly. And he's, okay. f of x is smooth and continuous. Okay, smooth and continuous at x equals 5. Yep, as we can see, they're nice and smooth from this point. All right. The graph of y equals f of x is shown below, where x is the horizontal distance from the start of the ramp. Yep. To, and the y is the height of the ramp, all lengths and measured in centimeters. Okay, so centimeters. Okay, the first part of the graph says, find f dash of x for from 0 to 55. Okay. Not bad. So what I'm going to do is I'm going to say f dash of x is actually equal to, I'm just going to write like a hybrid function. So because this is a constant 40, it'll just become 0. I'm going to put that, I don't need to put a comma actually, from 0, less. Why did I not put less or equal? It's because if you look down over here, now it becomes less of x less than 5. As we can see here, it's less than 5. So we can put less than 5. F dash, so for this one, we need to actually put on a calculator, this part over here, and find the derivative. So I'm just going to press Control N for this one. I don't need that anymore. Okay, add calculator. So what I'm going to do is define f of x as, so define f of x as 1 over 800 bracket x to the power 3 minus 75 x squared plus 675x plus 30375. Perfect. All right, so I'm going to just find the derivative. So that'll be f of x. Okay, so this is the derivative, which is written as, we can rewrite it as 3 over 800 x squared minus 50x plus 225. And we can write the domain. Okay, I'm just going to rewrite this domain at the back. So from 0 less than x less than 5. This one would be 5 is less or equal to x less than 55, because it's less than 55 here. So I hope that's right. I think so it is. Okay, that's it for this question. Find the coordinates of the point of inflection. Okay, one way to actually find the point of inflection, let me go to the calculator, is to actually find the f double dash. So find the double derivative. So what I can do is go over here, and to find the double derivative, it's this value over here. We use this. And I'm going to find the double derivative of f of x. And why am I just finding f of x? I know, because you got to remember that f of x is these two functions, because these two hybrid functions. But this 40 is useless because it's just from here to here. There is no point of inflection. Normally, the point of inflection should be around this point here, which is the rest of this graph. So that's why I've just let f of x equal that graph itself. So let me just enter. Okay, we get this. Now we solve that, and we want to let it equal to 0, comma x, and we get x equals 25. So at x equals 25, so at this point right over here, just at this point here, there is a point of inflection. So the coordinates are 25, and I'm going to put that back into the function. So f of 25, that will be 20. So 25, 20. Perfect. Find the interval of x for which the gradient function, okay, gradient function. This is where, I've seen this in a lot of exams actually, a couple of lately. The gradient function means that f dash of x, so that's the gradient function of the ramp, is strictly increasing. So when is the gradient of this graph strictly increasing? So what I'm going to do is, because I know, I'll go up on my cat, I know that the derivative is this. I'm going to copy this, and I'm going to go on graph calculator, and I'm going to paste it right over here. What I can see is, okay, and we actually want to restrict it, again, from restriction from 5. So it was from 5, that's all equal to x to 55. Okay, so we've restricted it, so it's this part here. So what we can see is, when is it kind of, so what do we try to find? Going to find when it's strictly increasing. Well, we can see it's always decreasing at this point. And as we get further and further, and it starts to increase, so it hits this point of inflection, which was over here, and then it starts increasing. So what we want to do is we want to find that point of inflection. So where we can go is to analyze graph, inflection point, which it should be around. Okay, so I'm just going to zoom in, zoom out a little bit here. So I'm going to zoom out. Okay, I'm going to zoom out. And I'm going to go to analyze, okay, inflection, so it should be around. Okay, not there, actually. So it should be a concavity, so it should be a minimum graph, if I'm not mistaken. Okay, yeah, here it is. It's a minimum part from 25 to where we restrict at 55. So the interval for which x of gradient is strictly increasing is from the interval is from x. It's an element of 25 inclusive to 55 non-inclusive, if I'm not mistaken. Yeah, because 55 is not included. That's very good. I think that's the answer. Okay, let's look at the next part. Find the interval for which f of x is gradient function is strictly decreasing. So when is it strictly decreasing? Well, it's strictly decreasing from 5. So x is an element from, if we look at the graph, it's from 5 to, wait, but isn't 5 just because, yep, so 5 till 25 inclusive, because 25 is included also. So yes, that's where it's strictly decreasing. Jack and Jill decide to, let me use another color. So Jack and Jill decide to use 2 trapezoidal supports, each of the width of 10. So yep, each of the width of 10 centimeters. Okay, makes sense. Yeah, we can see that the difference is 10. The first support has its left edge placed at x equals 5, and the second support has its left edge equals 15. Their cross sections are shown on the graph. Determine the value of the ratio of the area. So the area of the trapezoid, so trap cross section, to the exact area contained between f of x. Okay, so over the area of the graph, so the real graph. That's the ratio. So determine the value of the ratio of the trapezoid cross section to the exact area contained between f of x and the x-axis between x equals 5 and 25. So, yep. So we want to find this area here from here, this part here. All right. This part over here. And give your answer in percentage. So we want to multiply by 100 to get a percentage. Okay, so our area of the trapezium is quite easy to do. Again, use the normal formula. So what I'm going to do is, I know it starts off the difference. So what's the difference between the width? It's the 10. So you can say that 10 of f. So because it's still the f function, yeah, I'm going to go up. Yes, so it's the same function. So it's f. So I can say from f to, f till 5 plus 2f15 plus f25 multiplied, make sure you don't forget the half, is equal to, so I'm going to use my calculator for this straight away. That will be 10f5 plus 2f of 15 plus f of 25 times a half, which I'm just going to put 5 here, which we get 7.5. Now for area of the graph, which is quite easy to do, it's pretty much just the integral from 5 to 25 of the function f of x dx equals, so I'm just going to do it over here, okay, from 5 to 25 of f of x, comma x, which gives you 650. So come back over here, we can say 637.5 over 650 times 100 gives you, all right, so that would be, I'm going to put this over here, and put this one over here, times 100 gives you 98%, give you an answer in the percentage correct to one decimal place. Okay, so 98.11, oops, 0.1%. I hope that's right. So this one over here. Okay. So how long is, okay, we only have one more page. Okay, referring to the gradient of the curve, explain why the trapezium rule approximation would be greater than the actual cross-sectional area from any interval from x is an element from p to q where p is greater than 25. Okay, so let's just say that p, for in this case, is 25 to q. We don't know what q is, but some value. Let's have a look at the graph over here. I'm just going to rub these out. I don't need them anymore. So from 25, so we're saying from p to and onwards. So anything from this graph from this point. If we actually start drawing some maybe trapeziums, we can maybe start explaining this for. So it's saying that explain why the trapezium rules. So if we draw some trapezium, the trapeziums will have a greater area than the actual area. Let's try that. So let's say from 25 to 30. So first point over here. Let's draw. Okay, so it looks the same as the area of the actual graph. Let me try 35 now. We can see that the area of a trapezium is slightly getting larger. So what about in this part over here? Okay, we can see, if you guys cannot see over here, we can see that the area of a trapezium is becoming greater. Can you see how the yellow lines are larger than the actual line of the line of the graph, meaning that there's a greater area. Let's try this one at least too to double check. So from here to here. Okay, now you can see there's a lot of change here. You can see there's a big gap over here, meaning that the area of the trapeziums are much larger than the actual area of the graph. And yeah, and we can do the same for here too. And we can do the same for here too. Okay, you can see, yeah, that these lines over here, that the trapeziums are getting larger. And when's it getting larger? Well, it's actually getting, like, we can see it insignificantly from here, but it's getting actually more significant as we get into that curve, this curve like this. And we call that concave up, because it's like it's going up. So can you see that smile? We call it concavity, and we call that a concave up. And we can actually use that to explain it. We can say that as, let's just try to explain how we're going to explain this to get that mark. So we can say, okay, referring to the gradient of the curve. Okay, we can say Referring to gradient of the curve, explain why the trapezium rule approximation would be greater than the actual cross section for any interval where P is this. Okay. We can see that the gradient gets larger and larger. So as the gradient of f of x gets larger at because we know P is to say 25 to Q. So as the gradient of f gets larger at P and V, the graph concaves upwards. We can say that the graph concaves upwards, which is true. So it concaves upwards, leaving or making the top parts of the trapeziums larger. So as the gradient of the f of x gets larger, 25 to q, the graph concaves upwards, making the top part of the trapezium larger, making the trapezium rule approximation greater, say, than the cross-sectional area. All right, I don't know if that's right, but I don't know if I would give you the mark. I hope it does. As the gradient of fx gets larger, 25, the graph concaves upwards, making the top part of the trapezium larger, making the trapezium rule approximation greater than... Okay, yeah, I hope that gives you the mark, but I'm not too sure, yeah. I don't know why they put questions like this in the exam. They put worded questions in the exam. It's quite useless, I'll be fine. Jack and Jill, let's do question E. So Jack and Jill roll the toy car down the ramp, and the car jumps off the road of the ramp. The path of the car is modeled by this function. Okay, so f of x is our original function from 0 to 55, and we got a new function, g of x, is when the car goes out of it. So what's happened, let me just rub this off. What's just happened right over here now is that the car has left the ramp. So let's say this is your car, this is this box, this is your car. It's left the ramp and it just starts falling down. So it has this kind of, and it falls down here. So, and we are modeling that as, I believe, P of x. Okay, G of x actually. All right, G of x. All right. It says P is a continuous and differentiable function. Okay, that's important. So it's continuous and differentiable function at x equals 5. So they actually combine. They perfectly nicely fit. And g of x is given, but we have some variables b, c, and x equals a is where the car. So x equals a is where the car lands on the ground after the jump, such that p of a equals 0. Okay, so here would be the a value. Yep, and we can see that there. Find the values of a, b, and c. So b and c. How would we do that? Okay, what can we do? Well, because they tell us that P is continuous and differentiable, it means that when we sub in, so like let me just rub this part off here and just nicely draw it like this. So it's nice, it nicely fits into the equation over here. It's continuous, so it means that the value when we sub in f of 55, so this value over here, this part here, f55, it must actually equal to g55 because it's continuous. So if that, so I'll do that in my calculator. So we can say that, okay, let me just define g of x. So define g of x equals -1 over 16 x squared plus b times x plus c. Okay, so we're saying that f55 actually equals g of x, or g of 55. And we get this value over here. All right, so let me just write that here. So that will equal, this will 35 over 4 equals 55b plus c minus 3025 over 16. And they also tell us that it's differentiable, meaning that the actual f dash of 55 must equal g dash 55. And that explains it, because if we draw a tangent, so like a nice tangent here, oh, it's not that good, but like let's say we draw that tangent over here, the tangent would be the same for g of x, also would really be the same value. So yeah, which we can just do by our calculator. So f, okay, so what we have to do is, what's the derivative of f of x? And because this, and what's the derivative of, actually let me take that and just let me sub in x equals 55, and I want to find the derivative also of g of x when x equals 55. So, and we can equate these now. We can actually equate these two. So we can say, if we actually equate these, so if we solve this over here equals this over here, comma b, because that's the only variable we're left. Okay, we found out what b is actually. So b is 35 over 4. Now we can sub b into this equation over here to get our c value. So c will equal what? Well, if I go up here, take this here, and I want to say, let b equal this, and I can solve answer, comma, c. And we get, oh, big number, but, so it's, is that in decimal place? Oh, just, yeah, so c is actually equal to, let me just write that out, -4535 over 16. And that's it, yeah, the values of b and c. I hope that's right. Okay, I hope that's right. Okay, now I think that's the last question. Okay, is it? Yeah, it is. So determine the horizontal distance. So your horizontal distance from the end of the ramp to where the car lands, giving your answer in centimeters correctly decimal place. So we want to find, this is where the actual ramp ends. So this point here. And we want to find this horizontal distance from here to here. But we don't know the value of a. Okay, that's no problem, because we know that to find the value, so we know that p of a equals 0. Now we know what p of x is, so p of x is actually equal, because we know the values now, so we can say that what is g of x when c is actually equal to this and b is actually equal to that. It gives you this, so we can actually redefine the function. So define g of x to equal this new function here. Now, we can solve for a when we say p of a equals 0, and we can get the value of a. So we can say g of a equals 0. Why am I writing p? Oh my god, I'm supposed to write g. G of a equals 0. So a would equal, we want to solve answer, comma, a. And we get 2. So we get a equals 50 and a equals 89 point. Which one would it be? Okay, we know it must be greater than 55. So it must be between 55 and some value. So it has to be 89. So now we know a value of a, which is 89.10497. We can say that to find the distance, so distance is 89.1 0.0497 minus 55, this point here, which would be the end. So I hope that's right. So 55 equals, so this minus 55 gives you 34.10 centimeters to 2 decimal places. Okay, wow, that was a alright exam. It was an alright. It wasn't too bad. I hope those answers are correct, because there isn't any there isn't solutions to these questions, but I hope these are right. Yeah, if you guys think anything's wrong, please make sure to comment down below. I will make sure to look at it and fix it. If you guys enjoyed this video, please make sure like and subscribe and share it with your friends. And I also do tutoring. I do private tutoring 1-to-1. If you want that, you can actually just look at the link down below, and you'll see my email, and you can email me there if you want 1-to-1 tutoring. I hope you guys enjoyed this video, and yeah, please make sure to like and subscribe. Have a good day.